So the system that we're modeling in this lab is a hot dog store, and it has only one server, so it's a single server queuing system. So customers arrive at the store, they walk to the queue, they wait in the queue if there is any line, and then whenever the server becomes available, customers place their order, they wait until their hot dog is ready, they get their food, and they leave the system. So we're given some data about the operation of this system. As you can see here, the arrival rate is 20 customers per hour. Service times are triangularly distributed with a minimum of 1 minute, a maximum of 4 minutes, and a most likely value of 2.5 minutes. The queue rule is first in, first out, and customers' walking speed is 1 meter per second, and our system operates from 10 a.m. to 10 p.m., basically 12 hours per day. And the performance measures that we're interested in are server utilization, average and maximum expected number in system, and average and maximum expected time in system for our customers. I have completed my initial model, and I can run it in the interactive mode and watch the model run and basically see how entities flow and get processed in my system. So now that we have our initial model, we can go ahead and do some experimentation with it. So the first thing that I'm going to do before running my experiment is to set the run configurations. So I'm going to start my model at 10 a.m. and I'm going to set the run length to 12 hours, since we know that our system operates from 10 a.m. to 10 p.m. So now when I run my model, it starts at 10 a.m. and if I click on fast forward, you will see that it stops at 10 p.m. exactly after 12 hours. So we know that since we are dealing with random numbers here, one run of the model is not enough to make any decisions. So what we need to do is to replicate our model, and in order to do that in Simio, we need to go to the Project Home ribbon and create a new experiment. Now you can see the design or properties of your experiment here. You can simply set the replication number here, and I'm gonna set it to 200 as specified, and I'm gonna hit run, and the run is over. So I can now go back to my pivot grid and look at my simulation outputs. So what I'm going to do, I'm going to just focus on the model entity and server objects, and then just the population and resources, and the resource, sorry. And I don't care about holding time, resource state throughput. And what I want here is number in system, time in system, and scheduled utilization. And since I'm only interested in the average and maximum time in system, I can look at average, maximum, average hours, maximum hours, and percentages here. So now I have narrowed down my pivot grid to the 5 performance measures that I care about. So an important question that we always need to ask ourselves whenever we're building a model is that how do we know that a model is right? So in order to answer that question, we need to perform model verification. So one of the most common verification techniques is to compare our simulation results with an analytical model that we know is right. So what I've done here is that I have performed queuing analysis, and I'm not going to go over the details of it because we will have a whole lab on queuing models, but let's just assume that we know that this analytical model gives us steady state estimations of the performance of our system. So I know that at steady state, I expect to see an average 5 people in the system, and utilization is going to be around 0.83. So when I compare these values, I will see that my average number in system and average time in system in my simulation results are much lower than what I see here. So this can be an indication of a problem here. So either my model is wrong, or my expectation is wrong, or it could be because of randomness. So that means I haven't run enough replications. Now in this case, I have run 200 replications, which seems like a fairly large number, and I know that I haven't made any mistakes when I was developing this simulation model, and I trust the calculations I've performed here. So so what could be the problem here? It turns out that the problem is that my simulation model does not really correspond to this analytical model, because this analytical model gives me steady state performance. That means I need to run my model long enough to get to the steady state. Secondly, the assumption of the queuing analysis is that everything is exponentially distributed. So one thing that I need to do, the first thing that I need to do is to change the distribution of my processing time to exponential with the same mean value. And also, I need to go to my experiment properties and run my model for a longer time. So this time I'm going to run my model for 50 hours, and I'm going to reset and run the model. And the run is finished, and now I can go ahead and compare my values again, and this time I see that my values got much closer to my expectations, but still I'm getting 4.76 instead of 5 for number and system, and 0.23 instead of 0.25 for my time and system. So there seems to be a bias that makes these two values smaller than their expectation, and that's really because we start the model in an empty state. So when we run the model, the first few entities really don't spend any time in the queue because we start with an empty system. So we have this initial bias that we call initial transient, and we'll go over this concept later on. However, there is a solution to get rid of this initial bias, and that is basically by using something we called warm-up period. So if I go to my experiment properties, I can see that one of the properties is the warm-up period. So I can add a warm-up period here. So I'm going to add 25 hours of warm-up period, and what it does is that when I run my experiment, what Simio does is it runs each replication for 50 hours, but it throws away the results of, or the statistics that it collects during the first 25 hours of each run, in order to hopefully get rid of this initial transient bias. So now when I look at my values, they got closer to my steady state results, and if you want to get even closer to these expectations, you can go ahead and run your model for a longer time and increase your warm-up period, and hopefully you'll see that your results or values get closer to your expectations. But now I can tell that I'm confident that my model is right, because all my expected values fall within the confidence interval if you consider the half-bridge. And so now I can claim that my model is verified. Now I can go back to my model and basically change my exponential distribution for processing time back to what it should be, which is a triangular distribution with minimum value of 1, a mode of 2.5, and a max of 4. And now, since the only modification that I made after I verified my model was changing the processing time back to its original value, now I can still be certain that my model is still verified, since, or at least as long as I don't make any mistakes in putting the parameters of my triangular distribution in my model. So I can go back and basically, go back to my run and change my run length to 12 hours again, and go to, or let me basically create a new experiment here. So my second experiment will be based on 200 replications. So now I can run my model and report the number in system, and the average and maximum time in system, and the scheduled utilization.